due to solenoids. Before beginning this part, I recommend you have a look through the textbook, Knight, pages 813 to 814. That talks a little bit about solenoids, what they are, and how we use them. So a solenoid is a pretty important application of magnetic fields. It's something we use quite a bit, and we will use Ampere's law to find the magnetic field in the vicinity of a solenoid. A solenoid is really just a long, thin wire wrapped into a coil. If you want to picture what a solenoid looks like, first thing you can imagine is just a slinky. So if you had a piece of wire, you could wrap it into a coil. Okay. So I just did it by wrapping a paper clip around my pencil. Got a coil of wire. It's not a very nice solenoid, but it is a solenoid nonetheless. So a solenoid is a helical coil of wire. It's got the same current passes through the entire wire, through each loop in the coil. A solenoid can have 2 turns like this one, or it could have hundreds or even thousands of turns. Something we know about solenoids is that we get a uniform magnetic field inside of the solenoid, and outside the magnetic field is 0. So let's start to go through those things. First, let's decide on what is the direction of the magnetic field. So my solenoid here, it's got the current going up in the back and coming down around to the front. Looks a little bit like my paper clip here does. So there's my paper clip. The current comes in here. Maybe it's even hard to see 3D. So it comes in here and comes around. If I lay it flat like this, comes in on the bottom and up and around on the front. That's what the current in this solenoid is doing too. So if we want to find the direction of the magnetic field in the center, what we do is we put our thumb in the direction of current, and our fingers, our curled fingers, show the direction of the magnetic field. So I'm putting my thumb in the direction of the current, so up here in the back, and I'm curling my fingers so they come out through the center of the solenoid. You can even try and show it on a roll of tape too. So if this were my solenoid, my thumb goes with the current, and my fingers are asking what's the magnetic field at the center, and they come straight out. It's the same kind of right-hand rule we did when we did the magnetic field due to a single loop. What was the field at the center? We use the same right-hand rule, and we find the magnetic field going through the center of the solenoid. Okay, we can draw that magnetic field going through the center. So something that we stated here is that the magnetic field is the strongest and the most uniform inside the solenoid. If we have an ideal solenoid, that means it's infinitely long. Turns out the magnetic field outside is 0, and inside it's exactly uniform everywhere. So to think about how that happens, let's think about what the magnetic field around a solenoid actually looks like. So if you wanted to, you could set it up and trace it out with iron filings. The iron filings in this picture show that the magnetic field come down this way, and then they curl around and come back. So it comes down through the loop, comes back around, and loops down around this way. Just like the magnetic field around a bar magnet. And that was something we did around loops of wire too, how they looked like bar magnets. So for our short solenoid, the magnetic field comes down, comes around. So in this guy, you definitely have magnetic field outside. And if you remember your solenoid lab you did in Physics 1051, you might remember that. What if we had an infinitely long solenoid? Well, in that case, the magnetic field comes down around through the center like this, but it never ever gets out. It never ends. So the magnetic field can't loop back around, therefore the magnetic field outside is 0. There are another couple of ways you could prove that. Send me questions and I'll go through it if you're interested, but this conceptual way is not bad. Okay, so let's go back to our magnetic field of a solenoid. If we want to find the magnetic field of the solenoid, let's use Ampere's law. So we know the direction, we've got that established. Let's write down Ampere's law, which says that the integral over a closed path of the magnetic field is equal to our permeability of free space, the constant mu naught, times IN, where IN means the current inside the closed loop. Okay, so let's start with what is ds. ds is our path, and it's a closed path. So what is that path? Let's choose our path so that it's a closed loop and it's partially inside our coil and partially outside of our coil. So I'm going to choose this to be my path. I'm going to choose the direction of my path because it is a vector. I'm going to choose it to match the magnetic field inside. So then on the remaining sides it comes around like this. So our path is a loop, partially inside and partially outside. Okay, so let's go through the process. What is B dot ds around the loop? Let's try and figure that part out. So our loop has 4 parts. It has this segment, this one, and this one. Let's find B dot ds for each of those segments. We'll add them up and it'll give us the total value. So on the top, the integral of B dot ds is equal to the integral of 0 dot ds, because the magnetic field outside is 0, so that equals 0. On the sides, the integral of B dot ds is the magnitude of B, is the integral of the magnitude of B times the magnitude of ds times the cosine of the angle between them. So here our ds comes down, here our ds comes up, and in both cases, for the part that's inside, the magnetic field goes to the right. So that means that that angle is 90. So through the sides, the integral of B dot ds is 0. That leaves us with the bottom. The integral of B dot ds is equal to B times ds, the magnitude of B times the magnitude of ds, times the cosine of the angle between them. That one's to the right, that one's to the right. The angle is 0. So we've got the integral of B dot B times ds. B is a constant everywhere inside of our solenoid. So we're B times the integral of ds. The integral of ds will give us the total path of this length here. Let's call that length L. So we'll call the distance of the lower segment of the path, we'll call that L. Okay, so that takes care of this side of Ampere's law. Let's take care of this side next. What is I in? I in means the net current enclosed by our path. Well, if we want to know what that is, we have current I going through our wire, so it swings around. This loop has current I, this loop has current I, that one has I. So the net amount of current is equal to however many of loops there are inside there times the current in one loop. So N equals the number of loops. Okay, let's put those two things together and get an expression for the magnetic field inside of a solenoid. So the integral of B dot ds is 0 plus 0 plus B times L equals number of loops times the current in the wire. Let's solve for B. Oh, and I dropped my mu naught times mu naught. B is equal to mu naught times N times I over L. Sometimes we define a coil density that has the symbol of a lowercase n. That's the total number of coils divided by the length. It gives us the number of coils per meter. So our magnetic field inside a solenoid is mu naught times the coil density times the current through the solenoid The orientation of the magnetic field is given by our right-hand rule. So that goes through the magnetic field inside a solenoid with N coils and length L. In the next part, we'll do an example.